This is a fun-inspired problem from Art VITH with 5927, which is a definite integral from x equals to 0 to x tending to infinity, or 1 minus cosine of x over x times the square root of x. Very interesting problem. If you're not subscribed to our channel, we do really encourage you to consider subscribing to our channel. Your support would go a long way in giving us that extra visibility that we need. So how do we go about solving this problem? First, I would let u be equal to the square root of x, right? And this means that u squared is equal to x, and therefore 2u du can be substituted for dx. And so our integral here is the same as the integral from u equals to 0 to u equals to infinity. That goes without saying here, with the substitution of the limit of 1 minus cosine u squared over u squared times u. And then in place of dx, we have 2u du, 2u du exactly. And so this and that, this and that would cancel. And eventually you have the integration of, since we pull these two out here, we have the integration of from u equals to 0 to infinity of 1 minus cosine u squared over u squared. We can separate the numerators so that we have now 1 over u squared minus cosine u squared over u squared. Since we have this integral to the integral from x equals 0 to x tending to infinity of 1 over u squared minus cosine u squared over u squared, we can now express this integral of 1 over u squared as the derivative of 1 over u, right? And so using integration by parts for this portion here, we can say the integral of capital U dv is equals to u v minus the integral of v d capital U. And for this part, since our v is 1 over u, the product uv is going to be cosine u squared times 1 over u, so cosine u squared over u. So we can bunch the integral of 1 over u squared, which is negative 1 over u, and uv for this second part here. And so minus v is 1 over u, du is the derivative of cosine u squared, which is negative 2u sine u squared. And so we see that this and that cancel, and this cancel, so we have a positive here, right? Now going forward, as we said, we have now 2, because we pull this constant out here, the integral of sine u squared from x equals 0 to x tending to infinity. Then we can bunch these together so that we have limit on the upper side as u tends to infinity of cosine u squared minus 1 over u minus limit as u tends to 0 of cosine u squared minus 1 over u. Now with this, it's obvious because this oscillates between negative 1 and positive 1, and since u is a very big value, so this part here would just tend to 0. But the problem now comes to this, because with this, as u tends to 0, this is obviously 1. 1 minus 1 is 0. This is 0, so 0 over 0 is an interesting predicament. So we got to use what is called L'Hopital. When the limit for, let's say, x or u tends to 0, and if we have 0 over 0, we've got to use the derivative of the denominator over the derivative of the denominator, and then taking the limit at that point. So that's how we're going to approach it. Taking the derivative, we know that this tends to 0. The derivative of the numerator here is 2u sine u squared, and then the derivative of u here is 1. And clearly, as u tends to 0, we see that this also tends to 0. So this tends to 0, this tends to 0. And we are left with just the integral of 2 times 2, this 2 here and this 2 here, making this 4 times the integral from x equals to 0 to infinity of sine u squared. Now, this is the same as negative 4 times the imaginary part of the integral of e to the power I u squared. So using the Euler's expression, since e to the power I cosine to the power I u squared is cosine u squared minus I sine u squared, and the imaginary part is this. So it's the same as integrating this entire part and then only extracting the imaginary component, right? So going forward, we can now use the Gaussian integral. So you know Gaussian integral, if we have integral from x tending to negative infinity to positive infinity of e to the power negative x squared dx, this is equals to the square root of pi. But we're not yet there because we have this I here. So we do have to do some transformation. If we say let y to the power 4 be equal to negative u to the power 4, that means that y equals to the square root of u, and so dy is the same as square root of I du. And we're beginning with this. I didn't want to begin from I because then that means that we'd have to consider the limit where we have I infinity and all that. But with this, when the limit u equals or tends to negative infinity, y is positive infinity, and so on, vice versa. But since the integral is symmetrical, the answer is the same. So the limit doesn't really change that much. So anyway, getting back to our problem here, shifting things to the y domain, we have and I mean, let's go back here. So we had the integral from 0 to infinity, and taking both the negative and the positive domain, we took half of that, so 4 changed to 2. And here now, because we have shifted back where dy over root I is the same as du, so in place of du we have dy over root I, and we pulled out root I out. Now I to the power negative 1 is the same as e to the power I pi over 2, right? Because this is cosine pi over 2 plus I sine over 2. So I sine pi over 2 is 1, and so I, and then we apply negative 1 here. So negative e to the power. And then now square root of that is the same as e to the power negative I pi over 4, right? So, and this is 1 root 2 cosine pi over 4 is is root 2 minus I 1 over root 2. Okay, so and definitely this pi is square root of pi, the Gaussian integral. And as we proceed, we've definitely obtained that, and this is the same as that. And the imaginary part now is this part. And this is what we've extracted, root pi over root 2. If we multiply by root 2 by root 2, we definitely get 2 pi root 2 pi over 2, and that cancel. So we are left with the square root of root pi. The square root of 2 pi. And that's our answer that we were looking for. So a very interesting problem. I hope you're able to follow through and you enjoyed as we tried and solved it. Thank you until next time. À tout à l'heure, à la prochaine fois.